We just got done talking about the SN2 reaction. Now let's talk about the SN1 reaction. Remember, the SN2 reaction is a bimolecular reaction, so it would stand to reason that the SN1 reactions would stand for substitution nucleophilic unimolecular reaction. The kinetics of that reaction will be different, substrate structure will be different, stereochemistry will be different, and the mechanism will be different. Okay, so a few videos back we said there's two possibilities for a substitution reaction. You can have a concerted reaction where the nucleophilic attack happens at the same time that the leaving group leaves, or the leaving group can leave to generate an intermediate called a carbocation. And then this intermediate can undergo a second nucleophilic attack step to generate the product. So how would we write the rate equation for this reaction? How would it differ from an SN2 reaction? Well, let's look at a potential energy diagram to understand. In order to draw a potential energy diagram, we need to understand that this is a slow step, whereas this is a fast step, right? This is a slow step because we're creating a really high energy carbocation. This carbon lacks an octet, very high energy, so we have to go up a lot in energy to form that carbocation. Once it's formed, it is really reactive, so it undergoes a fast nucleophilic attack step to generate the product. Okay, so notice that's what we've shown in this potential energy diagram. We have two steps, so we have 1, 2 transition states. We have one intermediate, which is our carbocation, which is much higher in energy than our starting material, right? Because now the carbon lacks an octet, it's higher in energy, it's unstable. Notice there's a huge activation energy barrier for the first step and a very small activation energy barrier for the second step. So it turns out we call this first step the rate determining step, because this is the slow step that essentially determines the entire rate of the reaction. So if we're going to write a rate equation, we say the rate is equal to some rate constant times just the concentration of the electrophile. That's the only thing that's reacting in the first step. So now it makes sense why we call this a unimolecular rate, right? Because the rate is only dependent on one molecule, the electrophile. Changing the concentration of the nucleophile in an SN1 reaction has no effect on the reaction. So we can double the concentration of the nucleophile, the rate will be the same. We can triple it, we can quadruple it, we can half it. It's reacting with this thing immediately after it's formed. The slow step, which is determining the entire rate, is just dependent on the concentration of the electrophile. This makes sense, right? An analogy that we can use is sand funneling down through an hourglass. If you have a small constriction, that's going to make the sand come out slowly. Lower down, we can have a big constriction after the slow step. That's not going to affect the overall rate of sand coming through this thing at all, right? So the rate of sand coming down this hourglass is just going to depend on the slow rate determining step. So how does substitution affect the SN1 reaction? Well, notice tertiary substrates react quickly. So we'll call this fast. Secondary reacts pretty slow, and primary and methyl in this case are no-go. So we'll say tertiary is the fastest, followed by secondary, which is much faster. For all practical purposes, these don't go at all. So we're going to say just secondary and tertiary substrates undergo the SN1 reaction. How does this compare to the SN2 reaction? Remember, the trend is totally opposite for the SN1 reaction. Methyl is the fastest for SN1, then primary, then secondary, and tertiary doesn't undergo SN2 at all. So why is the trend reversed in this case? Well, keep in mind that's what's happening here is that we're generating a tertiary, secondary, primary, or methyl carbocation in the rate determining step. So the more that we increase the substitution of the electrophile, the more stable that carbocation that is generated, right? And if we look at a potential energy diagram, right, if our tertiary carbocation is lower in energy, that means the activation energy leading to the generation of that carbocation is smaller, which means that the rate is faster. So tertiary substrates undergo a faster SN1 reaction than secondary, right, because secondary carbocations are much higher in energy than tertiary ones. So the activation energy barrier leading to their generation is higher, which means that secondary would undergo SN1 slower than tertiary. What about the stereochemistry of an SN1 reaction? Let's say we start with a chiral tertiary alkyl halide. The first step as the leaving group leaves to generate a flat carbocation, right? It has an empty p orbital that has one lobe on one side of the plane and one lobe on the other side of the plane. The chloride ion could attack this lobe of the p orbital to give this product, or it could attack this lobe of the p orbital to give this product, right? If the chlorine attacks on this side, we get this product. If it attacks on this side, we get this product. There is no difference in energy between these two sides. They're symmetrical, so we get a one-to-one mixture of each one of these enantiomers, which is called a racemic mixture. So we say that SN1 reactions lead to racemization or loss of stereochemistry. If we start with something that's enantiomerically pure, we get a racemic mixture. We lose that enantiomeric purity. What are some other possible steps for SN1 reaction? Well, we can have proton transfer steps at the beginning or the end of SN1 reactions. We can also have carbocation rearrangements after we generate carbocation. Let's look at some examples of this. So remember, the first step is a leaving group leaves. This is not acceptable because hydroxide is a very bad leaving group. It's a strong base, and we want weak bases as leaving groups. But notice, if we protonate this first, so if we do a proton transfer step in the first step, then we protonate this starting material, we generate a good leaving group. Now this can leave to generate water and a stable carbocation. So let's say we take this alcohol, treat it with hydrochloric acid, and get this product. What would be a reasonable mechanism? First step would be proton transfer to go from a bad leaving group to a good one. That leaves to generate a tertiary carbocation, which then undergoes nucleophilic attack to give the product. Or, alternatively, we could have water as the nucleophile, chloride leaves to generate carbocation, and then water acts as a nucleophile. But look, we have a charged intermediate, and our product is neutrally charged. So what we need to do is transfer a proton back to the solvent, which is water. So water accepts the proton. Our compound donates the proton. So we have a proton transfer step at the end to give our final product. We can do this with an alcohol as well. It's the same series of steps. Leaving group leaves, alcohol attacks, the proton is transferred to the solvent to give our final product. What about carbocation rearrangement steps? If we take this substrate and treat it with sodium chloride, we observe this particular product resulting from a carbocation rearrangement. If our bromide leaves, we generate a secondary carbocation, right, which is less stable than a tertiary one. So an alkyl group can migrate to give the more stable tertiary carbocation, which is then intercepted by a halide to give our final product. So in summary, the SN1 reaction stands for substitution nucleophilic unimolecular. The kinetics is only dependent on the electrophile concentration because the formation of the carbocation is rate determining. The SN1 proceeds by loss of enantiopurity, meaning that we get a racemate. We get a one-to-one mixture of enantiomers. So be able to predict the stereochemistry for SN1 reaction, meaning that you're going to get two products, the R and the S configuration. Be able to draw potential energy diagrams for SN1 reactions. There are going to be at least two steps, and you're going to have one slow rate determining step with a high activation energy. You know that increasing the substitution of the halide increases the rate, so that the rate is usually tertiary is the fastest, secondary is slower, and then primary and methyl are pretty much no-go in the tertiary in the SN1 reaction. Be able to recognize when proton transfer or carbocation rearrangements will occur.